So in this section, we're talking about thermodynamics, and this reviews a lot of the information that we covered this week's group, but I just wanted to go over a few points just to make sure everybody understood the concepts. So what we want to look at first is the heat of reaction. You can ignore the little black box up here. For some reason it's eating my arrow when I import it into the app. But what we're worried about here is two different options. Is heat produced or is heat consumed in the reaction? Now producing heat is a lot easier to see. We can look at something that's considered exothermic. Heat is leaving the system, or heat is exiting the system, and in that case we see heat as a product. When we have something that is considered endothermic, heat is actually going into the system, and so we see heat as a reactant. So if I'm burning wood, then I'm seeing exothermic processes. It's releasing energy from the system, from the reaction, into the surroundings. When I look at something that's endothermic, I'm actually putting energy into the system. And so if you put a cold pack on your arm, where that heat is coming from is your arm. So you're actually removing heat from your skin, and that's why it feels cold. So we see exothermic and endothermic, and that's only worried about the heat of the reaction. When we look at the terms endergonic and exergonic, what we're looking at is talking about the energy of the system, not just the heat. So one thing when we're looking at reactions is this concept of randomness. Now, becoming more random or dispersing energy more really doesn't have isn't the only thing that we have to look at when we're determining whether a reaction is spontaneous or not. It's one of the things. You may have heard about this talked about as entropy. Okay. This tends to get covered in physics class sometimes, so you can talk about the entropy, and all it is saying, is the system becoming more random or less random? And so are there more ways to arrange those atoms? And so the easiest way to understand this is by looking at phase changes. When I look at a solid, what I see is that all the molecules or atoms are nice and neat and organized. I go to a liquid, less order, more random, different ways of arranging the atoms, more unique ways of arranging those atoms. And then when I get to the gas phase, what I see is that it's very random, lots of different ways for those molecules to be arranged, and they're dispersing that energy. And so that's kind of how we see that trend. We see a similar thing happening in reactions. If I were to look, say, at sodium chloride here, if I look at the solid, what I see is this array of sodium and chloride ions, sodium chloride, sodium chloride, and so on. When I form an aqueous solution, I see that those ions get separated from one another, and they are dispersed ultimately throughout this solution. So we're kind of making a more disorder, and so we're increasing the entropy of this reaction. We see something similar when we talk about iron rusting. We start with iron nails, for example, and when they react with oxygen, we form iron oxide. And so the compound ends up being more random than the element was originally. So when we're trying to determine the spontaneity of a reaction, we have to worry about two things. We have to worry about heat, and we have to worry about randomness. And the balance between those two things determines whether or not a reaction is spontaneous. So if we want a reaction that's spontaneous, what we need to have is a delta G less than 0. And for something that's non-spontaneous, a delta G will be greater than 0. And when we say something is spontaneous, what we mean is that it will react. The reaction will occur without outside intervention. And so it's not just the heat or just the randomness or entropy that determines whether or not a reaction is spontaneous or not. We can have something with a negative heat, and it balances out with its randomness to have a negative delta G, and vice versa. There's all different combinations of these values. We're not going to get into the quantitative aspects of this. What we're only going to worry about is looking at knowing that if we see a delta G less than 0, we know it's a spontaneous process, and we know that in order to determine spontaneity, we have to understand something about the heat and something about the randomness of that particular system. So very qualitative understanding of this concept. A concept that's frequently confused is the idea of spontaneity versus speed. We can have reactions that happen very quickly but are non-spontaneous, or reactions that are spontaneous but happen very slowly. There's no way to look at a reaction and just know what it's going to do without having some other information, some quantitative information about it. Now, when jewelers propose that diamonds are forever, that's not quite true. it happens to be a really, really slow process in how we get from a diamond back to good old carbon, like coal, but it does happen. So this is a spontaneous process, but it is a very slow process. So even in your lifetime, or even in yours and your children's and your grandchildren's lifetime, you're not going to see any appreciable change in any diamonds, but it is happening. And over time, it will convert back into that. So we see a very spontaneous process. It happens all on its own without any outside intervention, but it happens very slowly. So knowing whether something happens on its own and how fast it's happened are two different issues. So we talked about this a little bit the other day, and we covered it again in the packet, but activation energy is just that energy to get things going. So if you're not a morning person, you have a high activation energy, and so it's going to take longer for you to get out of bed. If you were a morning person and you have a lower activation energy, it's going to happen faster. You're going to be able to get out of bed more quickly because you have less of a barrier to overcome. We can look at another analogy using Legos. I can take two Legos and tap the bottom of one and the top of the other together all day long, but if I don't give enough energy, they're never actually going to stick together. And so I have to make sure that I have them at the right orientation, but more important, just as importantly, I have to make sure I have enough energy to overcome that barrier that exists for sticking those two things together. So activation energy doesn't affect the heat of the reaction, it doesn't affect the delta G of the reaction, but what it does affect is the speed of the reaction, because it lets us see kind of how big of a barrier we have to overcome. So this is the graph we were looking at in class, and now we see a different term. Instead of seeing something called exothermic, which was just talking about heat, we see something called exergonic, and what we're looking at is the actual energy of the reaction and that free energy change in the reaction, because it's that information that's telling us about spontaneity. And so we looked at some examples in the packets where we looked at dealing with the activation energy between an uncatalyzed process, which is what we see here in the green line, to a catalyzed process. And when we do that, what we see is that the energy of the reactants and products doesn't change, but what does change is the height of that peak, the activation energy. Now our activation energy is what I've represented there with that blue arrow, is from the energy of the reactants up to that top of that peak. Sorry, my drawing's not too great there, but it goes up to the top of the peak. So we have a lower activation energy. Now this is an exergonic process. On the right we have an endergonic process, still looking at our free energy change, but now we're looking at a positive delta G, or positive free energy change. And when we're looking at that, we're looking at a non-spontaneous process. That means we'd have to put energy in, we'd have to put something in to get this reaction going, or to let this reaction happen. All reactions require this activation energy. The magnitude of that activation energy affects the rate or speed of the reaction. So here we have our energy of our reactants going up all the way to our activation energy and ending at energy of our products. We can add a catalyst to this as well, and when we do, what we see happening is that we go up and then we go back down. Those are supposed to be overlapping there. And so what we see is that the energy of our reactants is the same, the energy of our products is the same, but the height of that activation energy peak or activation barrier is different. Now here for my catalyzed reaction, again I have it represented with the blue arrow there, but I see that the activation energy here is lower for the catalyzed process.